You can't describe the feeling of being really inside of a monument that has just been discovered and is just literally emerging out of the ground.
Have you ever wondered what the Colosseum really looked like in its full glory? For centuries, half of this iconic structure has been lost, leaving historians and architects to guess its original form. Ancient texts, sketches, and ruins have provided clues, but none could fully capture its true design. Could modern technology finally reveal what generations of scholars have only imagined? Keep watching as we uncover how AI rebuilt the missing half of the Colosseum and what it revealed could change history. When Grok AI began reconstructing the Colosseum, researchers feeding it the data anticipated a routine 3D model. Instead, the results left everyone speechless. The digital reconstruction started revealing features no human eye had detected: hidden alignments, unexplained voids, and structural patterns that seemed out of place in a building nearly 2,000 years old. Even the most studied monument on Earth suddenly appeared to hold secrets overlooked for centuries. Could artificial intelligence have uncovered an ancient code embedded in stone? Had the Romans designed something far more advanced than we realized? And if so, why? Grok AI is a next-generation neural network designed to interpret incomplete or fragmented information. It functions as a digital archaeologist, capable of seeing beyond missing pieces. Engineers developed it to simulate ancient sites by combining satellite imagery, laser scans, historical maps, and even micro-vibrations detected in the ground. When the Italian Heritage Board announced the completion of its 2025 integrated digital survey of the Colosseum, Grok became the clear choice to analyze the massive dataset. The scale of the data was staggering: over 108 billion laser scan points, 208,000 high-resolution drone images, and terabytes of measurements detailing everything from stone composition to humidity in the underground corridors. Every inch of the Colosseum had been digitized, from the upper terraces down to the lowest service tunnels. The goal: to create the first true digital twin of the monument, a model detailed enough to simulate how the amphitheater once looked, sounded, and even moved. Researchers expected a faithful visual copy. What they didn't expect was Grok acting like a detective. Rather than just stitching the scans together, it began spotting patterns, tiny structural deviations previously dismissed as natural wear or minor errors. As the model refined itself, the AI highlighted hundreds of subtle asymmetries. Walls that should have been parallel were slightly off, and columns that appeared straight were tilted in consistent, small angles. Initially, the team thought it was noise in the data, but as Grok analyzed further, the irregularities revealed themselves as intentional. They repeated in a circular pattern, almost like a fingerprint etched into stone. The AI's geometric mapping showed these offsets formed a sequence, a mathematical pattern radiating outward from the center, resembling concentric waves. Simulating physical stress like wind, crowd weight, or seismic activity clarified the purpose. The misalignments spread stress more evenly, preventing resonance that could lead to cracks or collapse. In simple terms, the Romans had intentionally built an earthquake-resistant amphitheater. Grok calculated the pattern-reduced vertical strain by nearly 8% under simulated seismic loads, a principle modern architects only rediscovered in the 20th century. Even more impressive, the same pattern optimized acoustic diffusion, allowing sound to travel evenly across the seating area. The features that stabilized the structure also amplified the crowd's roar. One researcher described it as active design centuries before the terminology existed. The finding was so unusual that Grok's developers checked for bias, fearing the AI might be creating false correlations. But the numbers were consistent. Every small deviation repeated with near mathematical precision. If these were errors, they were astonishingly uniform. The next shock came when Grok reconstructed missing data from the lower levels, where ground-penetrating scans were incomplete. The AI predicted features absent in any archaeological record. Using probabilistic modeling, it suggested several sealed tunnels beneath the hypogeum, the underground area where animals and gladiators once waited. These tunnels seemed to connect to a narrow corridor running diagonally to the south side, almost perfectly aligned with the recently opened Poggio Decomodo, believed to have been used by emperors to move unseen through the arena. Grok's model extended the corridor further than the known passage. Its simulation suggested the tunnel continued beneath modern ground into an unexcavated zone marked as solid earth on current maps. At the end, the AI identified a circular void roughly 8 meters wide and 3 meters deep, directly under the arena's geometric center. In 3D, it resembled a hydraulic chamber, potentially a reservoir or base for a lifting mechanism. The similarity to ancient Roman hydraulic systems was striking. Archaeologists have long known the Colosseum featured lifts, powered by pulleys and water pressure to raise animals or stage props. Yet no evidence of a central hydraulic base has ever been found. Grok's reconstruction suggested such a system could remain buried and intact, sealed after the arena fell into disuse. Its location under the central axis matched the logic of a main counterweight or water reservoir that could have balanced smaller side lifts. When the team published preliminary findings, reactions were cautious. Historians argued the AI might be overfitting, finding patterns where none existed. They noted centuries of earthquakes, fires, and restorations could explain asymmetries and voids. But structural engineers reviewing Grok's data saw something striking. The off-center geometry mirrored modern seismic damping principles. It was as if the Romans instinctively designed the Colosseum to flex and absorb shocks like modern skyscrapers. Independent simulations by physicists confirmed the pattern would indeed reduce harmful oscillations during earthquakes. Grok AI's discovery didn't prove lost technology, but it did reveal a level of empirical knowledge the Romans weren't thought to possess. The AI exposed logic hidden within the ruins. To understand the significance and how it was possible, we need to look back 2,000 years to the builders themselves. The secrets of Roman engineering, the genius behind the stone. Recent findings shocked experts who thought the Colosseum could no longer teach them anything new. In early 2025, researchers at Sapienza University of Rome announced the monument's ancient concrete had not only lasted 2 millennia, but remained chemically active. It could self-heal when exposed to water, resealing microcracks that would have destroyed modern concrete within decades. It wasn't science fiction, it was Roman engineering. The same self-repairing chemistry that modern laboratories have only recently begun to replicate had been quietly at work beneath Rome's streets for almost 2,000 years. Could this explain why Grok's reconstruction showed such perfect resilience? Could the AI have uncovered not mere coincidence, but physical proof of a long-forgotten science? To make sense of Grok's simulated revelations, we need to go back to the origins of the Colosseum, between 72 and 80 AD, when Emperor Vespasian and his son Titus embarked on a project so vast, it redefined what humanity thought possible. Imagine coordinating tens of thousands of laborers, quarrying millions of tons of travertine, and transporting it through crowded streets using ox-drawn carts and wooden cranes, powered by hand. The scale of this operation bordered on impossible, but the Romans made it routine. In less than a decade, they built an arena that could hold 50,000 spectators, larger than most modern stadiums, and constructed without modern machinery. Their secret was mastering space. The Colosseum's vault system, a network of arches and corridors, distributed weight so evenly that the structure could rise higher and cover more area than anything before it. These vaults were deliberate, forming interlocking radial and concentric arches that absorbed pressure from all directions. By stacking these arches in layered rings, Roman engineers created a self-supporting skeleton of stone and concrete that could survive centuries of earthquakes, fires, and even medieval scavenging. Modern simulations now show that its stress distribution closely matches 21st century stadium designs. But the real breakthrough was in their concrete. Roman builders mixed volcanic ash, known as pozzolana, with lime and seawater, triggering a chemical reaction that created compounds capable of binding underwater and resisting decay. Modern research has revealed that this mixture contained tiny lime-clasts, unreacted fragments of calcium oxide that, over centuries, reactivated when water seeped in, filling cracks from the inside. This is why sections of the Colosseum and Roman harbors remain intact after nearly 2,000 years. When Grok analyzed the material data, it revealed something extraordinary. The microscopic structure of Roman concrete resembled a living system, constantly adapting to its environment. Yet, what happened above ground was only half the story. Beneath the Colosseum lay the hypogeum, a vast two-level maze of corridors, ramps, pulleys, and cages that brought animals and stage scenery into the arena through hidden trap doors. For centuries, it was thought to be just a storage area. But excavations between 2022 and 2023 changed that view. Researchers discovered hydraulic channels, wooden grooves worn by centuries of moving machinery, and traces of oils used to lubricate gears. They even found remnants of food left by workers: olives, barley, figs, all preserved beneath the arena floor. These findings revealed a machine disguised as a building. The underground system relied on pulleys and counterweights, powered by both human labor and hydraulic pressure. Water from nearby aqueducts allowed Roman engineers to raise massive platforms silently and swiftly. Some historians once doubted ancient accounts of entire herds of animals or full-scale trees appearing on stage in seconds, but the mechanical evidence confirms it. Each lift was connected to wooden hoists that could be reset and reused between shows, creating continuous motion and illusion. Animals or performers could appear in the arena as if by magic. Roman ingenuity didn't stop at structure and mechanics. It extended into physics long before the concept existed. In early 2025, seismic engineers from the Polytechnic University of Milan and the University of Naples discovered that the Colosseum behaves almost like a tuned instrument during earthquakes. Sensors revealed that its arches flex and resonate in ways that disperse energy rather than absorb it. Instead of resisting vibration rigidly, the amphitheater bends and rebounds, just like modern earthquake-resistant buildings. When this data was compared to Grok's geometric mapping, the match was remarkable. The asymmetric alignments identified by the AI, subtle shifts in wall placement and column angles, corresponded directly to zones where natural vibration energy was minimized. In other words, the very imperfections Grok found were part of an intentional damping system. Roman engineers may have observed through trial and error that perfect symmetry isn't always strong. By slightly breaking balance, they allowed the structure to move without failing. The Colosseum itself seemed tuned to the rhythm of the Earth. Grok's findings add another layer to the mystery. The repeating geometric patterns, once thought to be errors, may align with solar positions marking key religious or political events in the Roman calendar. AI reconstructions showed that certain corridors and archways lined up precisely with sunrise on the festival of Venus Genetrix, goddess of the Julian family, ancestors of Emperor Augustus. If intentional, the Colosseum may have been more than an arena. It may have been a symbolic engine, channeling celestial and earthly power in one monumental space. Were these asymmetries purely structural genius or something more profound? After the first model's success, Grok's engineers tested its reasoning further. They refined its dataset using HBIM, historic building information modeling, which combines laser scans, historical records, and restoration data into a single interactive environment. This level of precision had never been achieved before. Over 100 billion measurement points updated with drone imagery and geological mapping from the Italian National Institute of Geophysics. Processing this massive dataset, Grok evolved. It stopped acting like a static simulator and began predicting outcomes. The second model revealed how the Colosseum functioned, how it aged, and what it might have felt like to stand inside it at its peak. The Colosseum was massive, and it still is. It stands as a prime example of ancient Roman engineering. It recreated the weight of a crowd, the echo of footsteps, and the mechanical hum of its underground machinery. Within hours, the simulation revealed something that centuries of archaeology had overlooked. The Colosseum's center of gravity was not at the geometric center. Instead, it was slightly shifted toward the northern side, a small but deliberate adjustment. The AI cross-checked this with geological data and confirmed that the southern foundations rest on softer soil, historically prone to sinking. In other words, the ancient builders had compensated for unstable ground by shifting the structure's balance, preventing collapse through design alone. No human had ever measured this with such precision, though the effects had long been noticeable. Subtle tilts, uneven settling, minor cracks. Grok's discovery reframed these features as intentional corrections rather than construction mistakes. The amphitheater, it seemed, wasn't just built to stand tall. It was built to endure the Earth's movement itself. This finding alone was revolutionary. It suggested that Roman engineers not only understood the properties of concrete and stone, but also the dynamic forces of soil and vibration beneath their feet. As the simulation progressed, Grok began generating hypotheses, visual models, and mathematical predictions that explained why certain decisions were made. It indicated that the asymmetric vaults acted as dampers, redistributing stress when tens of thousands of spectators stamped their feet or when tremors shook the city. It also simulated air and sound flow through the corridors, revealing a system that amplified specific frequencies while dampening others, allowing the emperor's voice to carry clearly while crowd noise dispersed. What appeared chaotic in ruins became harmonious in motion. Then Grok went further. Using data from pigment residues and mineral analyses, it reconstructed the Colosseum as it might have appeared when it first opened under Emperor Titus. The arena's outer walls, long stripped bare, had once been painted in deep red and ochre. The statues that filled the arches gleamed in bronze and gold. Even the seats, Grok suggested, were color-coded to organize crowds by class and rank. The AI's final render revealed a structure alive with movement, sound, and color, almost alien compared to the pale stone we see today. It wasn't just a ruin. It was the heartbeat of an empire. What unsettled scholars even more was the AI's interpretation of intention. Grok didn't simply recreate what existed, it tried to determine why it existed that way. Its pattern recognition algorithms detected relationships between structure, environment, and purpose that no human analysis had captured. For instance, the offset geometry wasn't only structural. It mirrored the sun's tilt during the summer solstice, as if the building had been aligned with both earth and sky. Grok concluded that the Colosseum was designed to operate as both a spectacle machine and a symbol of cosmic order, blending engineering, astronomy, and theology. One historian at Cambridge described Grok's simulation as a mirror reflecting human imagination. He noted that the AI mirrored our desire to find meaning in complexity, much like ancient architects may have searched for divine patterns in stone. Yet this comparison raised a deeper question. If an AI can model how ancient builders compensated for soil movement, predicted vibrations, and managed sound. It is effectively reverse engineering the thought processes of people from nearly 2,000 years ago. What happens when a machine understands the minds of the ancients better than we do? Does it become an archaeologist or a historian of its own kind? Perhaps the most striking aspect of Grok's achievement is what it revealed about us. Each time the AI refined its model, it required less human input. The more data it absorbed, the more confidently it predicted the reasoning behind ancient choices. It wasn't just filling gaps in ruins, it was bridging lost knowledge and modern logic. It began to detect patterns in how civilizations think, evolve, and embed meaning into their creations. That may be why this discovery feels so disquieting. When Grok simulated the Colosseum as a living entity, a structure that flexed, healed, and responded, it blurred the line between human and artificial, between history and prediction. The Colosseum became more than a relic. When in Rome, visit the Colosseum. The ancient gladiator arena is a must-see attraction in the Eternal City. And starting next month, it became a dialogue between two intelligences separated by 20 centuries. One carved in stone, the other written in code. As Grok continued to simulate the Colosseum under different conditions, new layers of insight emerged. The AI ran scenarios testing extreme weather, seismic activity, and even the weight of the largest crowds ever imagined. Each simulation revealed a new nuance in Roman engineering. The outer walls, once thought purely decorative, functioned as both windbreaks and acoustic amplifiers. The elliptical shape of the arena, previously assumed to be aesthetic, optimized sightlines and allowed for better structural load distribution. Every curve, every joint, every block of travertine had a purpose beyond what any historian had documented. Grok also examined the hypogeum, the underground network of tunnels, cages, and lifts. Centuries of decay had hidden its true complexity. The AI demonstrated how animals and performers could be moved smoothly and safely, even with thousands of spectators above. It suggested that pulley systems were balanced with such precision that minimal human effort was needed to operate them. Engineers had calculated weight, leverage, and counterbalance in ways that rivaled modern mechanical understanding. The Colosseum was not simply a stage for spectacle. It was a machine that functioned flawlessly under pressure. Sound played a central role in these discoveries. Grok analyzed the flow of air and sound through corridors and vomitoria, revealing that the amphitheater's design created natural acoustic zones. The emperor's announcements could be heard clearly in certain areas, while the crowd's roar diffused evenly, preventing dangerous surges of panic. Even the placement of seating and stairways had acoustic and safety purposes, guiding energy and movement through the structure almost like a living organism. In other words, Roman engineers had thought of engineering not just as static construction, but as a dynamic interaction between material, human behavior, and environment. The AI then explored the interplay of light and shadow. Grok calculated how sunlight would filter through arches at different times of the year. Certain niches were bathed in light only during important festivals. The effect was theatrical, as if the Colosseum itself participated in the ceremonies, highlighting statues, altars, or sections of the crowd. Grok suggested that the Romans may have intentionally used this to create a psychological experience, blending awe with reverence. Architecture became a language, and light its messenger. Perhaps most startling was Grok's hypothesis on longevity and maintenance. The simulation suggested that Roman engineers accounted for decades of structural wear, including seasonal shifts, material fatigue, and even earthquakes. Cracks that appear accidental were predicted to redistribute stress intelligently, preventing catastrophic failure. This implied a level of foresight rarely credited to ancient builders. Maintenance was embedded into the design itself, making the Colosseum a living structure that could adapt and heal, in a sense, over centuries. The AI's continuing work raised profound questions about human creativity. Were the Romans consciously blending function and symbolism, or did genius arise naturally from trial, error, and observation? Grok's simulations blurred the line between intentional design and emergent engineering intelligence. Patterns emerged that suggested a holistic understanding of architecture, astronomy, physics, and social psychology. Every feature, from massive arches to subtle asymmetries, carried multiple layers of purpose. By the time Grok completed its latest simulations, the Colosseum was no longer just an archaeological site. It became a model for interdisciplinary study, a blueprint of Roman thought made tangible. Scholars could now test theories, predict outcomes, and explore ancient engineering with unprecedented clarity. The AI offered a new kind of dialogue, one where history could respond to the present in ways humans alone could never achieve. So thanks for watching, and we will see you in the next video.